All right, so templates are the most significant tool, I would say, to write overhead-free abstractions. And so in C++, a little bit step back on C++. C++, you have functions and we have classes. Function is defined by a return type, a name, and a list of arguments. And the class is actually defined or declared as a class or a struct. And the definition of a class can contain type, data, and function members. The data members are the integers, floats, other classes inside the class. The function members are the methods of the class, and the type members are type defs and using statements of your class. So a function template is not a function, right? It's that to be clear. So you have a function. It takes two integers and adds them and returns x plus y. A function template is not a function, it's a template. So it's something that you use to construct a function. So in order to become a function, it needs to be instantiated. So the mental model here is that you take the type. For instance, I have a function foo that takes a template argument t. I can take a foo int and I can substitute the type int wherever t is found, and I can get the instantiation of that function. So it's basically a string substitution thing. It's just a mental model, but it works several times. So here I have a function. I have to define the template and the type name or class T. I tend to use type name, but you can also use the class keyword. It is a function that takes an argument t of type t, which is named x, and then prints x on the output. Now I can do foo inside the angle brackets specifying the t and 65. I can do foo and char and 65. In this case, I instantiate two functions. One is foo int, another one is foo char, and we pass 65. So the first one will print 65, and the second one will print the capital A letter, right? Because 65 is the ASCII code for the A. So I can have the same function here that behaves in a different way depending on the type I'm passing. I can also say foo with pi here, which is the question you had before. In this case, the argument is deduced. So this is a double. This t becomes a double. So you see tx. See, since x is double, then you have t is a double. Then you print a double. Then I do also a std string. This will take a foo instantiated with where t is the std string, and will print the std string. And this is a feature that really that helps you a lot. You don't have to write this. But in fact, this foo is foo angle bracket double, right? It's the same. So if you go and see, if you compile this object file and go and see what are the symbols that are available, if you don't optimize the code in this case, you will find that there are 4 different instantiations of foo. These 4 instantiations of foo will appear in a weird way, right? They will have some foo and then some other characters around. And we might actually see this in action. In our friend compiler explorer. It works, yeah, okay. Now, without optimization, maybe. Now, if I go to my generated code, I should see, usually after main, this is where the thing happens, I have a foo char, foo double, foo std basic string. So I have all these possible implementations. I have foo int, right? So foo int is just a function. It's the function that is instantiated. In some sense, the name of the function is not foo. The name of the function is foo bracket int. In linking time, I'm pretty sure you can do it with the Cobalt compiler. But the Mangle. I think, yeah, this is the Mangle. So now you should see the actual name of the functions that it is exported is this one. Say z icvt, z idvt, z3 foo. You see, foo is the name of the function. Z3 is the fact that it returns void. And here is just a long name with a lot of strange characters that tells you what the name of the function is. So actually, if you inspect this thing, those are the names of the functions that are called. So the fact that you can demangle and see the names in a human readable way is something that helps you. So the name of the function is really that really complicated stuff. And why it doesn't need to do that is because it has to disambiguate those functions. It has to be able to say which function you want to call. It's also why when you want to interface C++ and C code, you need to specify the extern C keyword to say, I want to call this function from C. Because otherwise the names will be a little bit intermingled. Because of the problem of overload resolution. You have the same function defined with different arguments. So the arguments are part of the name of the function. So. But yeah, this is just what happens. So you instantiate 4 different types of functions. It happens that if you then call again foo int again somewhere, it doesn't instantiate another copy of the function. It realizes, okay, I already instantiated foo int, I just call it. Right? So when we do overload resolution with the template, we go to the best option. So we have our foo function that's exactly the same as before, but now we define foo with something that takes a string, right? And so the last version here will not go to the template substitution. We'll go directly to this one because this one is more specialized. Being more specialized is just the better option. So if you provide that function, the compiler will select it for you. Order matters. If I have a function foo, it takes 2 types, t and u. Actually, did you know that you can just write this? This is a valid signature, a valid signature. So you don't have to provide names for these arguments. If you don't use them, you just don't put the names there. So some compilers are happier that way. Otherwise, they will complain that you're not using the variable. You just don't put the variable then if you don't need it. But it might be useful to have the function signature anyway. So now what I do after this, if I instantiate explicitly as a string and double, this will be the first argument is t, and the second one is u. So the first argument is string, the second is double. So it's a string and double, and I pass a string and double. If I do just the string, this also works. But if I do foo double, hello 4.5, this will force the first argument to be double, And then hello cannot be converted to a double. So this is a compilation error. They say cannot convert hello to const, which is a const char6 to double. So how does template argument deduction works? Suppose I want a function that converts any type to any other type. I want to pass the type I want to start with, and I want to get the type out. So I can say I want a function convert that takes a from type and converts to a to type. Now I can say template to and from. Now I can say convert int d, which means int becomes the return type here, and d, which is the argument, which is from type, is deduced. So d is double, and then I convert a double to int, but I can convert a double to char. Don't bother the fact that it doesn't make sense or whatever, it's just showing you what you can do. And then I can also say, well, I want the function pointer to a function that takes a float and returns an integer, and assign it to convert. Now convert is a function, and then I can infer that to is int, and then from is float. So this will actually work. So this will instantiate the function convert with the int float.
So with function pointers, you can deduce also the return type.
Yeah. So yeah, these are like this. So now, yeah.
It's not that ambiguous. I know it makes no sense, but we could also convert int to int. The compiler doesn't know. So like in that example, when you create a function pointer, how do you know that? How the compiler knows that the float refers to the second argument?
Because it's this one is the argument you pass in, right? It's a function you pass in. Do you know exactly when you do type deduction? It does it there. So now it sounds a little bit silly to put a to and from here, right? I want to do from to, not to from. So if I change the order of these arguments, I need to explicitly say the two values now, because double is the first argument from and is here, and int is the second one to. So if I cannot deduce d here at this point. If I do convert, if I write convert int to d, this will not work anymore, because int will be associated to the from, which is here, and then you try to do the d and get the d to be an int, and we'll say, well, there's something wrong here. But this will still, the function pointer thing will still work the same way. Just a little bit of exercise. So the first argument would be from, the second would be to, and we have to be explicit in both cases. In this case, exactly the same. So what we have seen is the function pointers. Function pointers, function templates. And now we can have also class templates. As function templates are not function, class templates are not classes. They are templates. So to be a class, to become a class, it has to be instantiated. We have to provide the type information. If we don't provide the type information, you get an incomplete type. So now I have a class. I call it temple name. This is the name of my class. And I put a template type name t on top. And now I can instantiate a member of type t. If this is int, this become int. If this you have a function call operator that takes, in this case, two integers and returns an integer if t is an int, and then does something with it. then now I can define my template name with a type, and I get a class name. This is like a type def. So my class name is a template name of integer, and I can instantiate an object of this class type. Again, text substitution. You take int, you put int, whatever t is, and then everything should follow from there. What you can do with C++ is partial specialization. So suppose that I have a struct x, and which is instantiated with two type names, with two types, t and u. But I want to implement a version of my class in the case in which the second type u is an integer, or in case the first type x is a float, right? So what do? This is called the primary template. Is the first class here. Is the first template is the primary template. Then I go to the specializations, partial specialization, in which I specify which are the template arguments which are still unbound. Just still have to specify, which is the first one here, and the second one is integer. In this case, I will say the first one is float, and the second one will be bound to whatever argument that my user passes me. So this syntax is can be a little bit tricky the first time you see it, but how it works is pretty simple once you break down the different steps. So if I want to instantiate x of char and double, I go to the primary template. This is x is this template here, t is char, and u is double, right? So I go here. Now I go to all partial specialization and say, well, is this guy better? Like, is double, is my second argument an int? No, it's a double. I have to convert it. Is my first argument a float? No. So this guy will go to the primary template, will instantiate the primary template. Because the other one are not better. They have to do a type conversion. So when you, as for the overload resolution, if template substitution is better than type conversion. So if he has to do type conversion, he prefers over template.
Could it be possible to name the second template different, not x?
Absolutely, yeah. You can name it as you want. Here you can say you can name it z, and this is z. Is that a question?
No, like, because for example, if I want to instantiate the first template, I got to do it through, for example, in the main function, you do it x char double, right? Then,
yeah.
Then if I wanted to call like the specialization, which is a template too,
Yeah.
you would do it just with one template argument, right? But it's still
No, it's like this. You see, it's like this. You see, x char and int. You put two values. Now it goes in and say which one is the one that matches better? Is the one where I have to do two template substitution, or this one is already int, so it will match this int with this int, and will pick up the second specialization.
I thought that the second template was calling the first one, but it's not like that.
No, it's not like that. The first template is really it's called the primary template. So it's something you have to have. This is something you must have in your code. And the other one are the specialization. And here you do pattern matching, really. So you match the best thing with your instantiation.
But how is that an specialization? Because it's just another template with the same name. I mean,
No.
the second template is not calling.
No, it's not a template, because you see here you are defining x, right? Now x, when you define x here, x is already defined here, right? You know this x is this x. But now you're saying this x, I will instantiate this x when my instantiation looks like this. When it looks like with the type t and an integer. I don't.
Say I have a template which is called base template, and then I have a specialization which is called derived template.
No, it has to have the same name. It's a specialization of the same class. So it's specialization of the same template. It must have the same name. It must be X. And while it is possible for these different X's here to have completely different semantics, different meanings, they can have completely different implementations, can behave completely different from one another. You can have the primary template to be a matrix and the secondary template to be, I don't know, a floating point number, whatever you want. It's always a good idea to keep these thing having the same semantics, right? It is X. It is supposed to behave like X. Yeah?
I don't know if I was first.
No, go ahead.
What if you want, for example, if we do perform some operation in the specialized float, and we know that we will do the same operation with double, can we specify in a manner that it takes float or double?
There are ways of doing it. You have to use some template magic, but you can do it. I have some examples later on. You can do it, yeah. But it's not straightforward. It's not something that the language really have you having. You cannot say float or double. Okay. You have to do some more things. Maybe you want to speak to the microphone.
For example, a most generic, the X up the top there says that given any T, any U, I will give you a concrete type following the substitution that's there. For the specialized ones, they're defining this, like specializations of the function by pattern matching, but there's still like a function from the type parameters to a concrete thing at the end of the day, and that's all it is.
Yeah, it's really matching the pattern you're putting here. So you're putting something that has a char and an int, and you find something that has an int. So it is a good match, right? And then you instantiate this implementation here. The second implementation will be instantiated. And actually, 1 second, is this specialization to not necessarily are compatible with one another, right? It can be really different types. You cannot maybe be able to copy one into another.
I was wondering here, if you wanted to instantiate with float and int, float as first argument and int as second, you would have to specialize against to exactly get it.
Exactly, yeah. This is where I'm going to go, in the next. So if I have a float and double, I go to this as a float, and you can see this as a float. And then if I do float and int, now I match these and I match this one at the same power. I have just the same kind of a type substitution I have to do. So this is a compilation error. This will tell you I don't know which specialization to pick. There was another question, maybe? So yeah, you can express this as a diagram where you have the primary template, which is the one you must have, and then you have the specialization for the first argument, the specialization for the second argument. But when both matches, you need the full specialization. And the full specialization, in this case, it comes with a special signature, which is this one. So you have template, and open and close angle brackets, and you specify float and int. Now you can see is like matching fully. So this float and int matches fully with this full and int. And of course, since this, you can put a space over here, or you can format it in a different way. It's not really string matching, but it's like it's slightly more general than that. You need to find that the first is a float, the second is an int, and you find which one's the best. But it's pretty straightforward if you think it this way. So the pattern matching can go as bizarre as you want. You can get really bizarre. So we have like the the same struct X as before, and now I want a specialization for my struct for the case in which the first type is just a type, but the second one is again an instantiation of X with T and U. So I have 3 template arguments here, W, T, and U, and this matches something which has a type W and then an X with a T and a U. All right? And now when I instantiating this guy over here, X int of X, int and float, I go to the primary template always. So I go to the primary template and say, okay, X, so T is int and U is X into float. Then I search for this pattern and say, oh, okay, well, look here. I have a case in which the second template parameter is an X type. So I will select this specialization for this line here. And this can be recursively defined. So I can X of int, X of char, X of int, and void. Void can be used as a template argument. And you can implement with this a list or a sequence of types. This is actually how BoostMPL implements list of types. And it's very ugly. You don't want to do it nowadays. There are better ways of doing it. But this works with the pattern matching. So now this X matches this one, and this one matches again the same specialization where the int avoid. So you're applying this recursively. Now this might take a bit of time to digest maybe. So if I'm doing foo of A now, so foo is a function that takes x tt and type t. Now I call foo of A. Should that work? It does. It does a still pattern matching. Since x is x double double, so it's x tt. Well, t is the same t, repeated twice. So in this case, foo of A calls this function, instantiate x double double. But if I were to do foo C, where C is this strange things here, where the 2 types are not the same, this will give me a compile error. So this will instantiate the primary template because it's not recursive. It's a int and float. So x int and float instantiate the primary template. This one we instantiate the specialization because the second argument is a type of X. Questions? This might take a while to get used to, but it's not really particularly complicated once you know the rules. The problem is you need to know the rules. What do we have here? Okay, yet another. Now, if I have a function foo, so now I have a function foo that takes t and t. So this is instantiated for the case where the 2 types are the same. And now I can get the case where the type is not the same. T and U are different. So now I can call foo of C, and this will call these overloads here. Usually you call specializations when you talk about classes, and overloads when you talk about functions. So you don't talk about specializing a function, but you talk about you create an overload. This is pretty powerful. You can really say, if these 2 types are the same, do something, otherwise do something else. And you can also, of course, not only 2 types, you can work with arbitrary types. So the structure of your type, you can basically encode the structure of your type and do pretty sophisticated things. In C++ 11, you can have a default template arguments for functions. You could have default template arguments for classes before C++11, but C++11 you can have it for the function. So you can have a function t, which has a result type, and you can say the result type is by default char. So when you instantiate std_cout foo65, then by default you return the static casted to char of x. So you get a 65 casted to a char, and you print the capital A in ASCII. But then if I do foo int 65, then then this is again returning A because it's the second argument. So here we're going to see int will be the first argument, and 65 will be deduced. No, 65 will be this one int. I'm confused. Yeah, and then goodness. And yeah, but still we'll print a char. And this one will print actually an integer. So we'll convert this to an integer, basically. And you specify both template arguments, the first and the second. Here the first is integer and the second is char, because I didn't specify it. And here the two parameters are represented as char, as integers.
Actually, the third sentence is not exactly true. So, it can be refined that
Is it on?
yes.
Yep.
So after default arguments cannot be after default parameters, it cannot be parameters that are not deducible, but it can.
They can be deduced.
Yes,
Okay.
it can happen that first parameter is default and other are deducible.
And the other are deducible. Okay, yep. I never implemented something like that.
It's actually used in standard library.
Okay.
For example, for make there is make array function where the first parameter is default equals void.
Okay, and then you deduce the rest for.
And the others are deducible.
Okay. So for classes, you can have again default arguments. Interestingly enough, is the fact that your template arguments are types usually, but they can also be constants. So they're called the non-type template parameters. So you can have an int, and you call it size is equal to 10. And that size is available at compile time as a value, as a basically something you can use by the compiler. So, and so when you instantiate my container with empty angle brackets, you will just take the default arguments here. Yeah, you just say, okay, whatever default arguments are, I define with double and size 10. So this is my container of size 10 doubles. And you need to specify this because my container is actually a class. It's actually a template and not a class. Now, in C++17, there are some tricks you can play and I'll show you, but they're just syntactic sugar. While my container of 100 will not work because the first argument has to be a type. So I have to specify the type. Here, the evaluation order of templates goes from left to right. So if I have a template, a class order, which is template T, and template type name U, which is defaulted to T : type, and X, which is defaulted to U : value, whatever. And in this case, this should work, because when I evaluate u, I know what t is. When I evaluate x, I know what u is. But if I do this, if I do type name t, and x is u colon value, and u is defined later on, u is a t colon type, this would not compile, because it doesn't know x before knowing u. So it doesn't know what u is. At this point, it goes here and says, well, I don't know what u is. I stop. So it is evaluated from left to right. It's probably something you never encounter, but it might be a problem at some point. Default argument and specializations. This is a tricky thing, pretty useful many occasions. There are certain facilities in the standard library that really relies on this. So now I have a primary template, which is my container double in sizes. And I want to instantiate my container. And then I have a specialization for my container for size 10 and one specialization for my container of size 15. I'm saying basically, I know that if size is 10, I can do a great job. Or if this size 15, I can do a great job. For other sizes, I don't care. I will have some basic implementation. This is not a so unearned thing, right? You might have your user will always use size 8 and sometimes size 300. And say, well, you know what? For those cases, it uses 300. It doesn't matter if it is fast or not. But I know that for 8, I can go very, very quickly. I can go really, really fast. So you can specialize for it. So in this case, let me see if I have the... So if I say my container char of 10, what happens? Well, the rule is that you always go to the primary template. So the primary template, you go and say the first argument is char and the second one is 10. So, but then you go on and say, well, if the second is 10, I have a specialization. So you go to the specialization. For this one, you say float and 30. You basically ignore these default guys and you just go to the primary template. And here you go to the T15. What happens here? What happens for the my container of int? Why? Again, you go to the primary template. The primary template tells you that the first T is int and the second is size 10. So this will try to instantiate int 10. But then int 10 has a specialization. So this guy will go to the specialization automatically. Okay? So it doesn't instantiate the primary template. It just substitute the size 10 because it's the default argument. And after it has substituted, it looks for the best match in the specialization order. Same thing here. My container with no arguments will instantiate a double 10 specialization because we'll put the first T to double and the size to 10. And after it does that, it search for the best matching implementation. As we saw, there might be non-type template arguments, like an integer. You can have integers, you can have char, you can have unsigned. Until C++ 17, you cannot have a double or floats. I think C++ 20 allows you for also floating point numbers, even though people are a little bit puzzled by this idea. But let's see. If it ever turns out to be useful, I don't know. I mean, it feels really odd to me, but this is what they are talking about. And why do you want to have an integer to be plugged in? For instance, as we saw before, maybe in my container, if I know exactly the size is 1024, I can do a great job in implementing the stuff. And that's good. You can specialize for that thing at compile time. So it's the compiler doing the thing, selecting the implementation for you.
Yeah. Related to what you mentioned, in the case before I was thinking what the container could be. just in the previous slide, I was just thinking what the container could be, and well, it comes to mind an array, right? That could be a typical container. Then, what would be the benefit of having like a constant a value template argument? That would be like a compile time, the size of the array. Well, better like a vector, because in vector you can have a compile time or like dynamic allocation. But then the size should be a constant expression. Otherwise, because let's put the example with a vector, right? Like a vector, you could define the size at compile time, or later on at some point you specify it.
The vector doesn't...
An STL vector.
Yeah, the STL vector doesn't have a const expr until, I think C++20 has a const expr vector. But otherwise, you don't have a const expr vector.
No.
I think C++17 doesn't have it.
I mean, like...
STD arrays, yes, but a vector, I don't think so.
Because what I wanted to point out is like, I've known that right here that if you, for example, have such a template where you define a value argument like size, right? Then that it would be beneficial if you know the exact size at compile time, because then you could have, for example, all that container like put on stack instead of on the heap. But then the size should be a constant expression, not.
Yeah,
like
sure.
this.
You have to know that the size. But when it is a compiled, when it is a template, it is a constant expression. It is known at compile time. You cannot put a variable there, right? So it's something you know at compile time, and you can do all the specializations. For instance, you're doing a fast Fourier transform. You can actually check that your number that you put here is actually a power of 2. There are ways of doing it. And if it is a power of 2, you have the best algorithm. If it is not a power of 2, well, I'll do something else.
Because what I'm not clear is like in this case, like we have a default value for size, but that doesn't mean that that's a constant expression. I mean, it is a default value, but that doesn't. I mean, I don't know if the compiler treats that default value as a constant expression. I wouldn't assume that.
So the default value is just there to indicate if the user doesn't tell me anything, this is the value you're going to put there. And that is a constant expression. That is a constant value. It is available at compile time. Okay. So there's no way for the compiler to say, okay, this is just something that will be defined at runtime. It's always compile time. So this trick of specialization only works for compile time specialization. And it's kind of tricky. So it can be tempting to say, if the array is small enough, I will instantiate it on the stack, otherwise on the heap. But there are some semantics involved there. So it's not that easy to get it running.
Things like standard, optional, and small object optimizations.
Yeah, small object optimizations, yeah, for instance, yeah. Yeah, there are cases with this actually happens. So you can do better if you know the size is small, maybe fits in a cache line, for instance. And there are ways of doing certain things, like if the size is less than the 226 bytes or something.
So you would use traits to like check for a condition, for example?
There are many ways of doing it. Actually, probably you won't do it. Probably you would do it with the const expr But you can play with traits. You can play with enable ifs and a lot of other tricks. So there are ways of which you can do it. I think I have a couple of examples where you can see this later on. The template arguments, which are non-type template argument, like in this case, can be actually useful. For instance, you can have even pointers as a compile time. So it's for instance, in the standard library, there is something which is a static int, where you pass the integer and you have a static const expr int value I. And then you can say stdc out static int 5 : value, which is this one. And then this code prints 5. There's no evaluation of 5. This is actually, static int 5. I know this is number 5 at compile time. And there are cases in which you want to play with these things. This is actually available in the standard library. But There is one thing that can be tricky to get, which is the SFINAE. Anyone heard about SFINAE? Good. Yeah, I know you know SFINAE. SFINAE is substitution failure is not an error. What does that mean? It means that when the compiler tries to instantiate a template or a specialization and finds out that they cannot do it because some type traits are missing, because the type does not exist, it silently ignores that thing. It will not tell you, oh, listen, there's something wrong here. No, it just goes by. Let's see why this is very useful. Let's say we have a class, struct x, and a t, type name t, and type name u, which is an integer, whatever. And then we have a specialization of this guy, and with type t, and the cases in which t is t column extra type. So in case my class t has an extra type member, and this type member will be an integer, for instance, and we will see how this works out, then I can instantiate this specialization. Otherwise, if t doesn't have extra type, this should be a compile error, right? I say, what are you trying to do? There's no extra type here. The compiler will not tell you anything. It just ignores this thing. And this is very useful. But tricky if it doesn't work as you want. So if it doesn't work in your favor, it might be tricky to get a reason why. So let's say we have this struct x, we have a type u and int, and have a specialization for type t extra column extra type. And we have a certain classes here, a struct a, which is using as a value type integer. This is a type def, right? It's a type member. Value type is an integer. Extra type is an integer. Extra type is a float, and extra type is a char. So what happens when I try to instantiate x with the a? I go to the primary template, and I say a and int, right? I try a and int. Then I go here and say a, and a column extra type. A doesn't have extra type. This is an error, so it will ignore this thing and will instantiate the primary template, right? So this employs SFINAE. The substitution failure is not an error. It simply didn't match. So fine, I will call the primary template. The second one goes to the specialization, because when I go to b has an extra type of int. So I will try to instantiate the primary template, x with b and int. Now I go here, b, extra type t column extra type, which is b extra type, which is int. Now I have an exact match, b int, like the primary template. So I will select my specialization.
You will prefer the specialization.
Of course, as before. If you have the specialization with matches, t extra type is an int, t is b, and now the primary template was a b and int. So now I have a specialization that matches. It will prefer the specialization. It's tricky. If it doesn't get right, if you don't get it right, it's tricky. What you can try to do is to I don't know. I will try just to put extra types, try to get the compiler to barf at me in some ways.
Maybe I missed it. What's the point of having like between struct A and B? The one is value type and the other one is extra type.
It's just to show you example, because when you design a class template, you don't know what the user will pass you, right? It will pass you something of type A or type B, and this type might have the trait that you want or not. If it doesn't, in this case, it doesn't have extra type. So even if I left this empty, right, it would have been the same, right? It doesn't have extra type. Then it goes to the default one. And the same here, you say, if I want to do B and char, what happens? So, okay, now let's go by in the order. X of C. So C has an extra type of float, but now I go to the primary template, right? X of C, primary template, I have C int. Now I go here, and here I want to say C float, because extra time is float, and this is not what I wanted to instantiate. I wanted to instantiate a C and int. So C float doesn't match. I ignore it, and I go to the primary template. And also here we go to the primary template. Let's go to the last one. So I have D. D is an extra type of char. And now I want to instantiate D and char. So I go to the primary template. X of D and char. Now I'm not using the default argument. There's a D and char. And now I go here. I have specialization with D, an extra type. Extra type is char. D and char. Matches with what I wanted to instantiate. So I instantiate the specialization. Yeah?
Why the C was eternally wrong?
All right. Let's go with the C, this one, right?
Because the default would be, okay.
Yeah, the default is not an int. I'm trying to instantiate an int, and then this guy says, no, I'm actually float, extra type. So this is basically all the tricks that all the rules that the compiler actually uses to find out what to instantiate and what not. And I see SFINAE is only employed in the first case, right? It's not something that is employed only there. And it's employed at the fact that A doesn't have a value type. So it is an error to access the extra type. But instead of telling you it is an error, it just ignores it. The SFINAE is employed in the standard library by enable if. And enable if is a nice feature. It was developed by this guy, Jaakko Järvi from Finland. And he came up with this idea. And it's really very simple. You can see that you want to say, I have my template, right? A type name T, struct A, and then I have a default argument void to an argument which I called capital void. It's just a name, and I want that to be void. Now, I can write something like, I want to instantiate A of type float, right? So it will be float. I go to the primary template. It will be float and void, right? These are what I want to instantiate. And then I go here. I say enable if is the same as t to integer. So if t is an integer and t is the type I'm passing here, so this is a float. So this is false. Is same column value. This is a type traits. Is the same t as int. This is true or false. In this case, it's false. In this case, it would be a substitution error. It will be an incomplete type. It cannot put the type here, and this will be ignored. So this is SFINAE. And then if not, is same t integer. In this case, t is a float. So this is true. It will instantiate type void as a second argument of my specialization, which is the same type that I wanted to instantiate here. So a float void. This is a float t, and this will become void. And this will instantiate this not int. Now there's a lot of details here. For instance, is the fact that you have a type name in front. Why? Because I'm accessing this std enable if with this template argument, which I don't know what that is. And I'm getting column type here. So I need to tell this guy this is a type. And this is column value is actually the static const expert value inside the class. It can be true or false. If it is true, this is false. If it is false, it is true. And then it returns void only if this expression is true. If not, the same is true. Then column type is void. Otherwise, it is invalid. It is an incomplete type. It doesn't exist. It's an error. It's a mistake. So you get the SFINAE. Did you know about this enable if? Who knew about the enable if? It's not really compile time if, but it's enable a specialization if. So it tells you that this specialization will be enabled if the predicate is true, which is compile time, and only. And it works with SFINAE. Basically, I don't know if I have the implementation of. No, I don't have the implementation. Yep. You have a microphone? You have to?
Implementation of std enable if is trivial.
Yeah, it's very simple.
There are two, basically, there are two specializations of it. First, if for the std false class that doesn't have type, and another is that do have type inside.
Let's see if we have the the possible implementation. Ah, yeah, here it is. Possible implementation. Here it is. It's actually embarrassingly simple. You have the enable if, which takes a Boolean and a default argument value, void, right? This is the primary template. Then we have a specialization. If the Boolean is true, then return T. Actually, no, it's not return, sorry. I'm thinking about meta class, meta implementation. So if the Boolean is true, I define a type, which is T, which in that case was actually void, right? Otherwise, I don't do anything. This is actually, yeah, so it doesn't, so in this case, it doesn't have a type member, so it will create it will give me an error message. Right, so in this case,
not even error message. It
will
produce a failure.
Yeah, so basically, if this was not, so if it is true, this type is in there, otherwise it's not there. So when I do column type, it doesn't find it, it is an error. It doesn't tell you it is an error, it just ignores this thing, and you get the SFINAE. Now in C++ 17, you have the const text per variable, so you can write something like this, enable it. You can avoid writing type name and column type, column value. You can say enable if t, std is same v, and void. And the important thing is this void is the same as the default argument. You can write float and float, right? As long as they're the same type, because you have to instantiate the same primary template in order for the specialization to be picked. Another instance of this is void t, which is even even nicer, I think. It's instead of enable if, which is verbose, you might actually use void t. And void t is a C++ 17 or 17. 17 feature is like that. That is the implementation. So this is a variadic template list. So this is a template that takes an arbitrary number of types. You can write void t of a double float char, class A, whatever, right? And all these types will be just expanded in a list of types. And then this void t will be just void. And this can be very useful because now, just want to go quickly in this example, otherwise it would take long. But basically what you can say, I want to check if I can add two numbers, right? I want to say, can I add? And I say decal type, or I can add if I have the plus operator in. Right? If I have the plus operator, then on class C. So I take class C. If C plus C can be added together, and here we can see decal val, because this plus operator might take references too, because I'm very open to nasty errors at runtime. And so I want to say, if class C defines an operator plus that takes whatever, which is not, which is basically also references, then the decal type of this expression is the results that I say can add, right? So I say C plus C returns an integer, then these can add become an integer. It's the decal type of this expression. And then I can simply say I have abstract the sum T. I abstract sum that takes a type T and will add T only the add of type T would return -1. But if the can add exists, so if I can do can add, if can add is not an error when you substitute the type, so if the plus exists and returns something valid, then I return A plus B. So I can do the add only if the add exists. And this is just again, it's a silly example, but it shows you that at compile time, you can know if something can be done or not. You don't have to wait till late, and you can say if the plus operator exists, in this case, it's basically saying if the plus operator exists, then use it, otherwise don't do anything.
Sorry.
Yeah.
Can you explain void T here again?
Yeah, okay. Yes, okay. Void T, so I'm here, and I say void, I pass it type T, and I say sum of T and void T. So when I call sum of T, we'll go to the primary template, and this will be T and void, right? This is what I want to instantiate. Now void T will have a list of types here, and the type will be whatever this can add type is. And can add T is the decal type of this. So if my T doesn't have a plus, this decal type will be a compiler error, but it's not signaled as an error, and so it will be ignored. So if you don't have a plus operator, you go to the primary template. If it has the plus operator, can add so void T of whatever type, so this type will exist, and void T of any type, of anything they can put there, will be just void. And so now it will be sum T of void, which is exactly the primary template that I wanted to instantiate. It's more or less clear? So these tricks are, it takes some time to get used to. But if you develop abstractions, they come pretty handy. Okay. So why do we want to use templates, basically? Suppose I have a template, I have a container class, right? My vector, whatever. And I want my container to basically be a container T of a vector of certain value T, and the value T is an integer. So I want my container to be a vector of integers, and I want to instantiate it, I call it C, and then I want to construct my container with the size S, and I instantiate my container. So when I do my container, my C, 42, will instantiate this my container with 42, which is inside will instantiate a vector of integer of type 40, of length 42. But now I can say, well, why should I restrain myself to integer, right? Why cannot simply say whatever type you want, and then I can tell, okay, my container in integer 42. And now this code is exactly the same as before. The resulting code is exactly the same, but we'll instantiate something with an integer type. And now the vector actually is not just a vector. It contains allocators, right? You can specify how to allocate data. So I can just put the allocator of my value type. So I take that I want to instantiate an integer value type, and I want an allocator, by default, the standard allocator of integers. And this will also work. So I can do my C42, we instantiate it, which is equivalent to integer and standard allocator of integer. And if I'm trying to allocate an integer with the standard allocator of doubles, this will be a compile error. But then the reason is that I should, because I have some redundancy here, right? I have to specify integer and integer in both places, so it's easy for me to make a mistake. And I don't want to make mistakes. So this one would not compile. But then I can use template classes. Just another dive into what templates can do for you. So instead of passing a type as a template, I pass a template as a template argument. And now this syntax is really like this: template, curly angle brackets, the list of types and value and non-type parameters, the keyword class, and the name. And this will be allocator. So now this allocator is not a type. It's really a template argument. Is a template. So now here I can say allocate. I have my value type, which is integer, and I want to allocate my value type with the allocator that takes my value type. So now when I instantiate my container, I can still do my container 42 because the allocator is standard here. Or int std allocator. Now, I don't have to specify allocator of integer here because I'm passing a template and not a type. So passing a template, this will instantiate the proper std allocator with the right type. So I cannot make this mistake to pass double here when I was passing int here. I will get the right type out of here. And this is the syntax that allows you to do it.
And this is valid in which C++?
Any. Yeah. This was valid in any C++, basically. I mean, I don't know before 98, but I'm pretty sure it was also before. It was before 98, right? It's always been there. It's one of the features that resisted with time. But you can also do my container be completely my container vector of int. So you implement your class where you would do my container with another container in there. So you can say type name container value type is the value type, the container is the container, and that's it. And you have to specify my container vector of int, allocator of int. And this is also another implementation, right? It's your choice. It might be better at times to have this one. Or you can specify even the container that you want to use inside more than also the allocator. So for instance, you can say, I want to allocate my container to integer, and I want to use a vector as a storage infrastructure. And I want to use an integer with a vector with this allocator in mind. And here you use template arguments again. You say, this is the template. I want a template with two template arguments, which is the vector as the value type and the allocator type. It's called, and by default, is vector. And this one is the allocator, which takes the value type. And then I simply allocate my CT container type of value t and allocator value t. So now my C42 is allocates an integer vector with the standard allocator. This will do exactly the same. But here I can put like list, deq, whatever. Right? I can put another container here, basically. Maybe not deq. And so you see that these template arguments do not have names. You can put names there, actually, but it doesn't matter, basically. So now you instantiate CT, and you pass these arguments here, which is the first and the second argument of the template argument. Okay, in C++ 17, here is another thing, which is the template deduction, the class template type deduction, which is an interesting feature. It might look like a simply syntactic sugar, but what you can do, you have a class, the template class T, and you have a constructor that takes T and instantiate the value, right? They pass X, and you construct X with the value passed to the constructor. Nothing simpler. You can do A of int x3, and you instantiate the class of integer. You pass the integer to the constructor. You construct your class. But in C++ 17, you can do A y3. In this case, what happens is that 3 is seen as an integer. So you deduce the type T of your class by the fact that this argument is an integer, and then you instantiate A of T. So this is equivalent to the previous line. Doesn't help much, but, sorry? Yeah, it does. I have an example. I have an example why it does. Maybe you have another one. So one example where it actually helps is when you have lambdas. A lambda is a function that you create in your code, right? You say, we'll see lambdas more in detail, but this is basically a function that takes two integers and prints out the I plus j, okay? This is the function. But now, what you should have done, if you want to pass that lambda to a class, you should have done b decal type of f, and a, and you want to pass the function in. The problem is that when you declare a lambda, the compiler will create a type for that lambda based on whatever rules the compiler has. So this type here exists, like in C++. Everything has a type, but you don't know what the type is. It will be an internal name for the compiler. So you need to do decal type of f and basically move. But instead, you can simply say b, put the lambda in the constructor line, and the class will be instantiated for you with the right type. You have other examples?
Yes, just want to mention that at the moment, so this feature addresses the inconvenience, for example, in the
maybe, yeah.
In the even in the standard library, there are for the objects like tuples and pairs. There are make tuple and make pair functions that just that kind of silly. They just delegate to constructor. And
is to do the template reduction.
And if you write generic code yourself, you always do the same thing. So for the templated class, you usually have the generator, the function that generates that, and it just delegates to constructor. And to address this design flow, this feature was there.
Yeah. Actually, what the compiler does basically is creating this generator for you. So when you have A or Y, 3, 3, 4, 7, the numbers, you will create a maker for that thing, right? So this is actually how it is specified, right? So you have a class template, T, and then the T is the argument here. Then I will have a make A that takes an integer, and it's basically doing behind the scene what every developer has been doing, so having generators for the class. I want to go into a lot of details. It's going to be pretty late, so. But basically, so template meta programming. We're not going to talk about template meta programming, but I want to give you a hint of what is possible. So in classes in C++, can have a different kind of members, which are like static member, static functions, constexpr function static, constexpr data type, data member and member functions. And meta programming is a technique that hopefully will be outdated, where you basically use templates to do computations at compile time. Now there is the constexpr keyword and other mechanism that helps you doing a better job. But let's say before C++ 14, I would say it was quite tough to get a good constexpr thing. There's too many limitations, I think, for the constexpr keyword. But basically what you do in metaprogramming is the manipulating types at compile time. So you instantiate templates and you process these templates at using the template rules. I say that typical, if you write one application, you don't typically need this kind of stuff. It's only when you develop a library, when you develop some interfaces to give out to the world, where you really need to sometimes to resort to this kind of techniques. So a class can have so a class X can have public, private, or protected specifiers. And then you can have type members. When you say using type and you define something. You can have also template types, like template type name T using type T, which is the alias templates. And you can have a static const int and static constexpr int. And this is how the class look like. And now, suppose that I want just to show this small example. I have a struct, which is a factorial. I call it factorial, which takes an unsigned char in input. All right? As a non-type template arguments. And now I want to say std out factorial 5 and a column value. I want to print this value out. What does this thing does? It has a specialization for the case in which n is equal to 1, right? So I go here and say static constexpr. So this is a constexpr compile time available data member for this class. I call it value, which is n, this number here, times factorial n minus 1 and column value, right? And this is like unsigned now. I'm passing, it's not char, it's unsigned. Because I'm casting, I think, yeah. And then if it is 1, it just value 1. So what does it do is that n times factorial, again the same class instantiated with a smaller number. So if I pass 5, it will be 5 times factorial 4 value. Factorial 4 value will go here with 4 times factorial 3 value. Then will be factorial 3 times factorial 2 value and 2 times factorial 1 value, but factorial 1 value is 1. So here we get 120 at compile time. So if you look at the generation code for this, you will see a line which is move L 120 into register, right? And I think this is very powerful. So
I missed the last part. What you mean? The explanation is the line that is moved. I just missed that last part.
So here's factorial 5.
Yeah.
Column value. So you go to this value here, which is equal to n times factorial n minus 1.
Yeah.
So this goes into 4, 3, 2, 1. And here we have factorial of 1.
It's kind of a C.
Yeah, it's kind of the base on the recursion, right? You go here, you don't call factorial anymore, it's just 1.
Yeah.
And then you have 5 times 4 times 3 times 2 times 1. And then you get 120. Okay. So if you go to the compiler explorer with this code, you will see this instruction at some point, and it says move 120 into there. So this is done completely compile time. Something that now you would do with const expert, and we will see more about the const expert keyword. But this is something you could do with just using templates. Integral constant is something that we saw before also, that you can get the integral constant value. I want to show you also an example. STD rank is a function that is a functionality which is available in the standard library. That given an array, you get the rank of it. So if I have a 3-dimensional array, the rank is 3. If it is a 4-dimensional array, the rank is 4. And I can implement this using templates. And so I have a struct rank. I have a struct rank, which is basically an integral constant of size t 0. If I'm passing a size integer, the rank is 0. A scalar, rank 0. A 1-dimensional array, rank 1. And then I go here and say, if my type t that I'm passing is a tn, so it's an array type, then I go and compute the rank of t, because the rank int 3 of 4 is t4, where t is int 3. And so it is a recursive expression where you basically strip out one of these dimensions at a time until you end up with a base type, and then you can compute your rank. So std rank is implemented like this in the standard library. And this one you could do it basically only with template things. And then you want to make sure that it is legal also when you don't specify the size, as it is legal in C++. Okay, well, maybe this is a little bit too... Yeah, let's select first example. Let's go to alias templates. So alias templates as a type def on steroids. Type def, you can say type def blah blah type, and then you define that you have an alias for the type. Right? Alias using statements like this, using integer equal int. This is just equivalent to a type def. It's just a different syntax. But the using keyword, you can use the templates too. Template type name t using type vector t. Right? So when you use it, you say, give me the type of Boolean, and this will be type of bool. This will become a vector of bool. All right? So type is a vector of bool. So so I can say type double x100 is equivalent to vector double 100. You can use default arguments, many arguments, all the tricks in the books or for the classes basically work with the alias templates. There is a little subtlety though, because an alias template is still a type def, so it's not a type, it's just an alias for something else. So in this case, I have a function that calls size off, right? I want the size off I define my vector, my vec, which is an std vector with my allocator t. And my allocator t is a class that I have defined somewhere. But this is an std vector with this allocator here. Now I want a size of function that takes a const ref to my vec, which is this guy here, that returns the size. And I have also something to say, well, if the user is not using my vec, but is using directly vector, I want to have a specialization for std vector t, my allocator t, and then I want to return size. Now, this is a compilation error because my vec is nothing. My vec is exactly identical to std vector t, my allocator t. So I have two functions with exactly the same signature. Having the same signature, the compiler says, I don't know which one I should take. They look exactly the same to me. So here again, you can have like functions that are never picked up because, for instance, here I want to have something which is a v of integer and call my vector of integer here, but it will not be picked up because the std vector has two template arguments and not one. So my vec is std vector and is not a type. If I define my vec as a class, then I can do that. But if I define it just as an alias template, it would not. And I think we probably stop here. And maybe tomorrow morning we go on with the variadic template stuff and then move semantics, and then maybe we have something more, we can learn something useful. Any question? Was it useful, surprising? Too difficult, too many details? I would say too many details.
It'd be always good to have like examples on the side. I guess if you explore that at some point.
Yeah, I have examples in the code. The problem is that if we start making examples of everything, it would take them 2 months. So yeah, we have to balance a little bit. So the idea is to give you more, basically just give you the information just to know that the things exist. So you are not surprised when you encounter a compiler error or you start looking into something. Maybe you can take a look at the slides and say, well, let me search more about this argument. This kind of stuff is not something you learn in 3 days, right? You need to practice. You need to work on some real stuff in order to get used to it. I think it's useful to at least know that these things exist, right? That you know that something is up there, and it's very rich and powerful. And I don't expect that you go home now, you go to your hotel or whatever, and start writing templates like crazy. I don't expect that. But at least you know that these things exist, and you can start thinking about interfaces, APIs, etc. And hopefully by the end of the course, you will have enough examples and enough studies to see these things actually, because these are the basic stuff, right? The basic mechanics. And now we need to see how these basic mechanics can be used. And we will see with the examples and stuff here. All right. Thank you, guys. Totally not necessary.